Okay. So physics, very important. And I just want to go over some examples to try to convince you, to motivate you, to get you excited about physics. So here are some examples. Maybe you know that device here. Scott, yeah? Defibrillator, what's your name? Orlando. Okay. So it's a capacitor. So we're gonna see that next semester. So it's a device that you're gonna charge with a voltage source. So one will be connected to plus, the other one will be connected to minus, about 200 volts. So you are storing energy here inside the electric field, and you're gonna discharge it inside the heart. So the heart is an electric device hoping to wake up the dead, almost dead, or to make the heart beat at an even pace, right? So physics, very important for the medical field. And then GPS is another example. So to have the right location and the right time, you need at least 4 satellites. Okay, so these are GPS satellites. But what people do not know, most people do not know, is that to have a good GPS system, you need to take into account general relativity. General relativity developed by Einstein. Turns out, as you move away from the Earth, the gravitational field is going to get weaker, right? The Earth doesn't pull as hard. And the consequence of that is that the time will run faster. So our time on Earth is running faster than the time of the GPS satellites, right? So the software engineers working on the system, they have to fix that. Otherwise, how much is that? You're going to lose 45 microseconds a day. So you have to take in account general relativity. So you need to understand how it works. So it means that if you are in a black hole, so you have a very strong gravitational field, what's going to happen to the time relative to our time? The time will stop. The time stop. Okay, so if I look at someone going into a black hole, the time of this person will stop. Okay, as you get closer and closer to the black hole, the time will run slower, slower, slower. Inside the black hole, it stops. So I look at this person, I see the person frozen in time, like this, right? But for the person in the black hole, he's already dead. Yes.
Is that the same? Could you say the same thing with stars?
Yeah, so as you get closer to the star, gravitational field increases, right? And then the time will slow down. Because when the star is collapsing, if gravity wins the game, it will become a black hole. It can become a black hole, right? So all that is physics. Sometimes it's not always for the good of people. Depends on your frame of reference, of course, depends on your opinion. But here is another example of applications that will be the atomic bomb. My God, what's your name? Giovanna?
Yeah.
Huh?
Yeah.
Satyan?
Santiago.
Santiago. Okay, got it. So that would be this one was called the Fatman. I know they had nicknames. I guess they were not politically correct at the time. So they had the little boy and the fat man. So this one was the fat man, which was the plutonium bomb, ended up on Nagasaki. Little man ended up on Hiroshima. Very good, right? That little man was a uranium bomb. Fat man was worse. It was a plutonium bomb. Okay? So whether you think it's a good thing or a bad thing depends on your frame of reference, as you can see here. Okay? Talking about frame of reference, of course, we will work only with Cartesian frames of reference, X, Y, Z, and the coordinate of that point will depend on which frame you are working with. You won't have the same X, Y, or Z, depending on the frame. Now, you have very weird effect if your frame of reference is rotating. So, for example, we live on a rotating frame of reference. So you see here, the Earth is rotating. So it's going to sweep out the same angle wherever you are every second. But that point here and this point there, they don't have the same speed. Very good, right? Because higher latitude, the distance will be smaller than at the equator. Consequence of that is that, let's say you are located here, Congo, maybe you want to send a gift to your friend here in Norway, and you send it in a straight line. If I'm outside the Earth, it's going to be a straight line. If you are on the Earth, it's going to be deflected to the right. So this is called Coriolis force. So I just have a demo. So talking about demo, one thing I do for this class, if you come up with a good demo, okay, that has to do with what we are doing, obviously, and you make a video, you send me the video. Don't copy me, of course, but I will give you extra points on the text, depending how good is the video. Okay, so this is my Earth. It's a flat Earth. So it's a rotating frame of reference for someone living here. Okay, I am in a non-rotating frame of reference. So I am here. Maybe it's in Congo. I'm sending a gift here. So from my point of view, in my frame of reference, I'm going to make a straight line. Okay? You with me on that? And the thing is moving counterclockwise. So let's see if I can do that. No, it's not rotating because I put a tape here. That's why professors usually they don't do demo, because always something is not going to work. Oh. Okay. So I make a straight line, right? So you see what happened? In my point of view, I did a straight line in my frame of reference. But in the frame of reference of this species here, it was deflected to the right. You see that? So from the point of view of this person, everything happens like you have a force. I don't see that force. I see a straight line. There is no force. But this person will see a force. We call that a pseudo force because it's not the same in all frame of reference. So that's why on Earth, okay, you have hurricane, and the hurricane in the northern hemisphere will go counterclockwise. So if you have a mass of air, of course, I forgot to do that. So if you have a mass of air, it will go from high pressure to low pressure. Very good. So the I here is low pressure. So you see it's going to be deflected to the right. And this one, the mass of air, also deflected to the right because of the Coriolis effect, and so forth, and so on. So consequence will be hurricane. Right? Isn't that cool? In the southern hemisphere, they will spin in the other direction. It will be clockwise. Okay? Same weird effect in any frame of reference that is rotating. So we will talk this semester about circular motion. So for the pop quiz on Thursday, maybe I will ask questions like this, just conceptual questions. So anyway, you've heard about centripetal force or centrifugal force. So it's just an introduction as well. Centripetal force means looking for the center. Centrifugal force means away from the center. Whether we talk about centripetal force or centrifugal force depends on the frame of reference. Okay? So if you are inside here and it's rotating, so it's like a merry-go-round, what you're gonna feel if you are on a merry-go-round? Is it centripetal or centrifugal? Very good. Centrifugal force, right? It seems that you are pushed outward. And because you are pushed outward, the wall or the floor is going to push back. So that's a way to simulate gravity. From my point of view, looking at you from the outside, I don't see the same thing. I'm going to say Newton's first law says an object wants to keep going in a straight line at a constant speed unless acted upon by a force. So the body here wants to keep going at a straight line at a constant speed because it was spinning. No, it can't. It's going to be pushed toward the center. So from my frame of reference, it's going to be a centripetal force, right? Centripetal force. So there is this masterpiece by Kubrick. It's called 2001 Space Odyssey. Masterpiece. Okay, it's a great movie. It's amazing. The guy was a genius. Okay, and he's the first one to display to the public how to simulate gravity. So in the movie, it's very, very famous because you have this music, the Blue Danube, a very famous music. Like if you want to go fall asleep, it's great. And you have a space station here, and people will walk on the wall because it's spinning, right? So it's simulation of gravity. It's a very famous movie, 2001 Space Odyssey. Masterpiece. They talk about AI, by the way. It was like he was predicting the future. Don't know if you've seen the movie. There is an evil computer called HAL, H-A-L, HAL. What come after H? I, A, after A, after L. So that will be IBM. That was before Microsoft, right? IBM, they're the one who built the first computers, right? How smart is that? If you like the cartoon Futurama, in one of the episodes, you have the evil computer, it has a red eye. That's what he talks in the movie. That was a 1960 something movie. I forgot the date. 1966, because I was 1 year old. That's how I remember. Okay, so for those who are going into software engineering and they want to code video games, very important to have your frame of references right. And that's a glitch, of course. And you need to know how to go from one frame to the other, from the eyes of the character here to the eye of the player, the gamer. For that, you need linear algebra. And Galileo is very famous to have said all the laws of nature in the universe are written in math. So you really need math. And if you're doing robotics, same thing. Correct? When you code for robotics, those arms or the robots, you need to go from one frame to the other one, to the other one, to the other one. So even if you go to software engineering, it's very important. So this semester, we're gonna cover mechanics, Very important for civil engineering. You don't want the bridge to collapse. You want to understand equilibrium, static, meaning it doesn't move. And you want to make it right, especially in those ugly towers in Miami, very ugly. You don't want them to collapse. You don't want to be in trouble. If you go to mechanical engineering, you want to understand how machines work, and especially levers. So levers, very important for anatomy. Okay, all the human body uses levers. So levers, and the one who understood that was the Greek. So it's not Aristotle. Aristotle was more like a philosopher, but it's a good try. The one who said that if you are in a fluid, you're going to be acted upon by a buoyant force. Start with an A. No, Archimedes, right? Archimedes, right? And actually, they always remember Archimedes because, the story, he was taking his bath and Eureka, he found the force, the buoyant force. But he's the one who said also, give me a lever long enough and I will be able to lift the world. So this is called the load. And he's pushing, this is called the effort. And this is called the level arm. And he used it for war, because at the time they were always going against each other. He lived in a city called Syracuse, not in New York, right? But in Sicily. So I guess it was belonging to Greece. And you see, he had this machine here. You had a huge claw, okay, to lift the enemy, the ships of the enemy. So a lever can do two things. It can amplify the motion, like this, or it can amplify the strength, like that. So it makes you stronger. So that's what he builds. Levers are everywhere in the human body. So I'm not someone very skinny, as you can see, but I can lift myself, right? I don't go very far away from the ground, but I'm lifting myself. So that means there is a lever here that makes me stronger. There is always a price to pay. I have to walk a lot, over a long distance, and the body will not lift by very much, but you are amplifying your strength. This lever here amplifies the distance. Okay, all those machines very important for mechanical engineering. Of course, you all do bikes. You know how to bike. You have gears. So this, when you go from small to big like that, you amplify the torque, but you decrease the speed. Right? So low gear means you go uphill, so you're going to amplify the torque. High gear, you amplify the speed. So we're going to talk about torque. Torque is the tendency of a force to make a rotation happen. You have wheels and axles as well, so this is also to amplify the force. So that's why we need physics. Talking about Archimedes, we're going to talk about forces. So forces are vectors, so you will need some trick. You need to know how to find the components of vectors. So you might want to review your trig as well. Forces here, you see they have an application point. So for example, here you have a boat. You have a center of mass. What is applied? What is the force acting on the center of mass? Gravity, right? So we're going to talk about the weight. Okay? It depends. I think women have a lower center of mass, men have a higher center of mass. But for stability here, you want to make sure that all the load will be at the bottom. So you want to have the center of mass lower than the center of B&C. Okay, so this is the buoyant force. Each body submerged in a fluid will be acted by an upward force. So you see here, you will have a torque, and then it will be fine. This is not fine. That's not an engineer who went to FIU. Okay, that's not good. It means there is too much stuff here versus there. So it's going to do that. Okay, so you don't want that to happen. Physics also very important for sports science. So here, center of gravity, buoyant force, you're going to be stable. So I might be saving your life right now. If you are lost at sea, you want to have this position here and you don't get tired. Here, you always have to fight against the torque. Here, it's static equilibrium. Just hoping that there is no sharks, or because this is very temptation for a shark, I guess, but otherwise you will be fine. Okay, any question? So, for the medical field, some of you will take the MCAT or go physical therapy. I think they have, now you can have a PhD, physical therapy, exercise science. Physics is very important. So you have something called Bernoulli principle. It turns out when the fluid is moving really fast, so for example here, you see to catch up the fluid has to go really fast here relative to there, the pressure is going to go down. So here is an ideas for a demo. You take a piece of paper here, you're going to blow on top. What do you think is going to happen? So this is low pressure, this is high pressure. What's going to happen to the paper? It's already bent. So here you have low pressure, here you have high pressure. Air goes from high pressure to low pressure. So what's going to happen? It's going to lift, right? Because any fluid moving faster than the like here, for example, it will introduce a low pressure, right? So that's called Bernoulli principle. You see the fluid here has to move really fast to catch up. The pressure here will drop relative to there. So very important for human body. So for example, here, if you have a plaque, I don't know, fat or whatever it is, the blood has to move faster. So it's going to be low pressure here, high pressure on the outside. Consequence will be something like that. Okay? This you already know, right? Because you all took chemistry in high school. So if you decrease the volume, what's going to happen to the pressure? It's going to increase, right? All those molecules, they don't like to be packed. They hate each other. They are boxing like crazy. So pressure will increase. And if you increase the pressure, if you increase the volume, the pressure will decrease, right? So that's how we can understand how the lungs work. You have a muscle there. So if you increase, right? If you increase the volume, because you move that muscle down, the pressure inside will go down. So the air from outside will rush inside. Does it make sense? If you decrease the volume, so you push the muscle up, the volume will decrease, the pressure will increase, and the air goes out. You want to make sure that, and it's all physics. So don't say, I am in biology, I want to be a doctor, I don't give a blank to physics. No. You need to understand that. You see here, you want always to have a pressure lower than inside the lungs. Because what's going to happen to the lungs otherwise? It will collapse. Very good, right? It can happen with a virus, inflammation, accident. You can have a collapsing lungs, which is very bad. They have to inflate again. So you see the pressure in this bag outside has to be always lower than the pressure inside. Okay, so if you go to sports science, physical therapy, things like this, it's all physics. We have three systems. One is the fluid system with the heart and the blood. Here, I guess. And then you have the mechanical system with the bones, the ligament, the tendon, and the muscles. And then you have like the electric system, right? Electric system with the nervous system. So it's all electricity, signal, electric signal flowing through your nervous system. Okay? Okay, if you are in sport, okay, sports science, they say science, they should say physics. It's all physics, okay? Biomechanics is physics, sports science should not be called science, it's called physics. So if you are playing baseball, tennis, cricket, ping pong, you all know that there is a trick. So here you have that's, I don't know, baseball maybe. So it's coming this way. So the air is going to flow that way. Do you agree? So if you make the ball spin, which is called the spin this way, it's called the top spin. You make it go spin this way, what's going to happen to it? It's going to be deflected down. So that way your adversary is going to miss the ball, right? Tennis, they do that. So the ball is going in this direction. If you make it a backspin, very famous in baseball, if you make it a backspin, the opposite will happen. It will be deflected up. Why is it happening? We're going to learn about Newton's laws and third law, which is not intuitive. For every action, you have a reaction opposite. So because the ball is deflecting the air up, the air say, no. You are deflecting me up. I'm going to deflect you down. For every action, you have an opposite reaction. So the ball here, it's going to go this way. It's going to go down. If you have, so this is top spin. If you have a back spin, it will be the opposite. So in tennis, they do that a lot. So the opposite side will miss the ball because it's going to go down this way or it's going to do that way. But you have to practice. I cannot do that. So about videos, as I told you, you can make videos at the gym. For example, a lot of things to do at the gym, make short videos, and I will give you extra credit. So I did this one with someone very muscular. So he took like a roll, you know the roll in foam, right? He made it top spin, and then he went down. And then he made it back spin, and he went up. So I did it quickly. I don't know if you can see that. Very muscular, right? So he makes the things back spin.
Yeah.
It went up.
Yeah.
But now, if you do it the opposite,
Oh, that was down.
top spin, it will go down. Up.
Oh, that was down.
Okay, so that's the type of demo you can do.
Golf ball with backspin.
So very famous in cricket, they do that. So backspin.
That exerts a vertical
It's
force,
going
a
up.
lift
Isn't
force
that
on the
crazy?
ball that keeps it in the
Backspin
air for a
goes
longer
up, top
time,
spin
and therefore it
goes
travels
down.
further. A tennis golf ball with backspin.
So backspin,
That exerts a
oops,
vertical
it goes
force,
up.
a lift force on the ball that keeps it in the air for.
Okay. So sports science, physics, very important. Also, here you have something interesting that will be for the end of the semester. It's called angular momentum. It's the spin. And the spin is always conserved unless there is a torque involved that will change your spin. So, for example, in this, what this person is doing, he just spin the lower body, which is easy, but not easy, but quote unquote easy, with the skateboard, and the upper body will spin on its own, right? Or you spin the upper body and the lower body will spin on its own for conservation of momentum. So if he stretch the arm, he spin in one direction, the lower body will spin in the other direction because of conservation of spin. To understand how those people they get to make a turn, they use something called counter steering, which is absolutely not intuitive. So you see here these handles are fused to the bike. So if they push in this direction, it's going to turn in that direction. Okay, it has to do with angular momentum, not intuitive. So if I push this way, the bike on its own is going to do this. That's how they do it. And it has to do with physics. It's fascinating. So it's called counter steering. If you push this way, it's gonna turn that way. That's why you have so many accidents with the bikes, the electric bikes, the electric scooters, because they say, oh, I want to go this way. So they turn this way and the thing goes like that. And they are not ready for it. So physics can save your life. Okay? And then, any question? So we'll talk about friction. So very important if you are an engineer, you want to design the best key ever, you want to decrease friction. And so that you need to understand friction, air resistance as well. So if you want to decrease the resistance, you make that aerodynamics shape, right? So air resistance, the air will just flow like on top of it, so it won't slow down the car. Because again, for every action, you have a reaction. So if you push on the air will push back on you. But if you make it that shape here, it's hard for the air to push on it. Is that clear? You have to be very, very careful here. Because remember, what's going to happen if the fluid goes really fast here relative to the air? What's going to happen to the pressure? Yes, right? The pressure is going to decrease here relative to there. And what's going to happen to the car? It's going to flip, right? You have to be very careful with your design. That's why we need very good engineers. Not like in the NASA. Did you hear what's happening in NASA? There is 2 astronauts stuck in the International Space Station. Isn't that terrible? Huh? Boeing. Yes, Boeing. You're right. It's they were supposed to be 8 days, and now they're going to be stuck for 8 months. Not years, but not weeks, months. Isn't that terrible? Oh, yeah, I will be so pissed. I mean, terrible. Because you know what's going to happen in the space station? You are floating, right? It seems that you are weightless. It doesn't mean that the earth stops pulling on you. That's not what's happening, but you float. So when you walk, like I'm walking now, I'm doing walk against what? Gravity, right? Like if you do exercise or Pilates using your own weight. So because they cannot do that, what's going to happen to their muscles? Exactly, they're going to have loss of muscles and they're going to have loss of bones, right? The bone density is going to decrease. When you are old like me, it's called osteoporosis, right? Density goes down, but that will happen too. And who's going to save the day? SpaceX, right? Elon Musk. So he's supposed to go and get them, but not before February. That's terrible. Maybe that's why he can open his mouth so much, right? They need him. Maybe after he gets the astronaut, it will be different. I don't know. So anyway, just to say that you need physics to be a good engineer. We'll talk about heat. Now, we are not going to cover that. I have a playlist, but that will be for next semester. However, we'll talk about energy. So heat is energy in transfer. So even if I'm not working out, I'm losing energy. Energy is flowing out. And one way is through radiation. So because you are alive, thank God, you are warm. So what type of radiation you are losing? So it's not visible light, because if I turn off the light here, you're not going to be shiny. So it's not, so here it's artificial colors. They do that with the software. So you have wavelength, right? You have gamma ray, X-ray, UV, visible light, infrared, radio waves. We emit infrared, okay, heat waves. And we have a very small wavelength, a peak wavelength. And that, using that, you can tell a person's temperature. So that's how, for example, God forbid for cancer, for example, if someone has cancer somewhere, not far from the skin, you're going to have more heat emitted. So you can detect the cancer using infrared sensors. We're going to learn about watts. Watt is the unit for power, right? It's the amount of energy produced per unit second. Watt. So all that physics doesn't really work when it gets to metabolism, because it depends on your age, if you are insulin resistant or not, but in theory it should work. Calories in equals calories out, which is only working if you are young. Not really true after that. So anyway, we are like a 100 watt light bulb. So we emit the same energy per second as a 100 watt light bulb. So question for you, so you don't fall asleep, 100 watt light bulb, how come if I touch you, I'm not going to burn myself, even though it's like a 100 light bulb? Yes?
The surface area?
Surface area, that's what you want to say? Yes, exactly the same thing, right? So it means the same energy will spread out over a larger area, okay, even though it's the same energy. And you can even compute how much calories you need. So 100 watts for 1 day. In 1 day, how many hours? 24. 24 times 100 is 2,400, 2,400. So it's about 2,400 calories on average, because watt hour is an energy of, it's a unit of energy. So 1,000 watt hour is 1,000 calories. Okay, thermodynamics, we'll leave that for chemistry. Okay, but it's the industrial revolution. Very important for mechanical engineering. Heat goes from hot reservoir to cool reservoir. And you can, using that, you can harvest motion, you can harvest work. That was the whole idea of when they developed thermodynamics in the 19th century, is to make the machine, heat machine, the heat engine as efficient as possible. Okay, so that will be for next semester. Electromagnetism. This is a great Michael Faraday. Didn't go to school, didn't go to college, still was a genius. He figured it out. how to make electricity, the same electricity we are using here, just with a magnet and a closed loop. Genius. Electromagnetism. This is a maglev. It's a magnetism levitation, also physics. Very important here for civil engineering. You need to understand resonance. Okay, so if you shake something at the right frequency, so this is called the resonance frequency, it's going to amplify the motion, and that's what you can get here. If you don't have engineers going to FIU, for example, very famous example, Tacoma Bridge in Washington State. That's what happens, right? There was a bridge, and the wind was pushing the bridge at the resonant frequency, the natural frequency, so the bridge went higher and higher and higher, and it breaks. So this is called resonance. Okay, so for that you need to study wave property of waves, right? When you fall in love, for example, that's resonance. If you talk to your friend about everything, your friend will be fine, but you touch on that subject, they go off the roof. That's called resonance as well. Okay, so just to conclude, we have come a long way in a very short time. Okay, so that was before transistors. So transistors were developed in the 1960s. Kind of by chance, they were working on a hearing aid. So that was only 5 mega. You see how huge it was? So the first IBM computers were like that big and not as efficient or powerful than my smartphone, right? And then they went to that, and from here they went to here once they figure out solid state and how transistors work in a very small amount of time. So technology is amazing. So that takes you to quantum physics, the physics of the very small. If you want to understand solid state, hard drive, and transistors, you need to understand physics. So the way it works, it's gaps. Okay, so it means doesn't move, that will be a 0, it moves gap, it will be a 1. So 0, 1, 1, 1, 0, 0, 1, 1, 1, that's a digital information. Okay, so every 10 years, every 2 years, the number of transistors is multiplied by 2 on a microchip. Okay, you want really fast. So this is a log scale. Okay, then you have modern physics. Einstein, 1905, got the Nobel Prize, not for general relativity, not for special relativity, but for the photoelectric effect. He understood that light can behave like little particles, bundle of energy. Those particles of light can kick out electrons from silicon, for example, and that's how you have solar panels today. So this is called the photoelectric effect. And finally, beware of pseudosciences. Don't believe whatever you read in the news or social media. So this example I love because it comes from a French astrophysicist, Etienne Klein. I say it right because he's French. And so there is this space telescope. I'm sure you heard about it. It was launched in 2021, so not long ago. It's called James Webb Telescope. Engineers have been working on it for decades. Okay, so a long time. It's an amazing piece of technology. Okay, and this astrophysicist, he posted this picture and he said, look, that's a picture taken by the James Webb Telescope. It's a picture of Proxima Centauri, which is a red dwarf. It's a star. It's the closest star from our sun. And people say, wow, amazing, look at the details. And actually, it was a slice of sausage. So Then he apologized and he said, I'm sorry, and this is French, but he posted a real picture. So this is the cartwheel galaxy. So I thought it was a funny example. So beware.